All right, let's polish off this two population variance tests problem. Problem 1 of 1 in the mastery practice problems and solutions for this last module, module number 13. So here it is. As you can see, pretty simple problem. It says for the sample summarized below, test the hypothesis that the two variances are equal and do so at a significance level of alpha equals 0.05. So you've got the table, gives you a sample variance, gives you a sample size. That's kind of all the information you need for sample 1 and sample 2. There's the information. The first question says write down the null and the alternative hypotheses. So if we look at the top, it says test the hypothesis the two variances are equal. Generally when you see that, there's no information about whether the one variance is bigger than the other. So the two hypotheses becomes one, the two variances are equal, the null hypothesis, or that they're not, the alternative hypothesis, and there you have it. That means that this is a two-tailed test, right? And what is the formula for the test statistic? In order to answer that question for these problems, you look back at the alternative hypothesis. If it is that H1, that sigma 1 is bigger than sigma 2, then the test statistic should be sigma 1 squared all over sigma 2 squared, okay? And if it's the other way, then you just have to be aware of which side of the F distribution you're doing this test on it. And generally people are, it's suggested that you put the larger of the two variances on top. So again, if the alternative hypothesis was that sigma 1 is bigger than sigma 2, you would make the test formula S1, the larger of the two, is greater than S2 squared. You'd make the test statistic F is equal to S1 squared all over S2 squared, S1 being the larger. If instead the alternative hypothesis was that S2 is bigger than S1, you would make the test statistic S2 all over S1. You'd always put the larger of the two sample variances as in the numerator. In this case, sigma 1 is not equal to sigma 2. Again, you would put the larger of the two in the numerator, and the larger of the two is S1. It's 25 versus S2, which is 10. So what's the value of the test statistic? It's S1 squared divided by S2 squared. That's 25 divided by 10. That's 2.5. And then maybe more importantly, the numerator is N1 minus 1. N1 is 7 minus 1 is 6. And the degrees of freedom for the denominator is N2 minus 1. N2 is 17. N2 minus 1 is 16. You're going to need that for the next question. The next question says, great, you just drew a line in the sand with your test statistic. Well, you really just plotted your test statistic mentally in this F distribution. Now let's calculate the p-value, the area in the tail to its right. You're going to go to F CDF. The lower bound is 2.5. The upper bound is 1e to the 99th. The numerator degrees of freedom is 6. The denominator degrees of freedom is 16. When you run that, you'll see that the p-value is 0.067. Now, what's the conclusion? What we were doing was a two-tailed test. So we took the 0.05, the 0.05 significance level, and we broke it up, one in the right tail, one in the left tail. There's no actual tail. There is no tail on the left-hand side since the F distribution stops at 0. But it's 2.5 so I'm comparing that 0.067 to 0.025, and as you can see, P is bigger than 0.025. That means you fail to reject the null hypothesis, and the variants are effectively equivalent. You might say there's no evidence that they aren't equivalent. Okay, very good. That's the way that goes. I'll leave it to you to do the rest of the problems like this. All right, thanks a lot.